about the way we choose to regulate in this country. It's not a decision that's made by particularly by the enforcing authority. It's a decision about how the legislation works. No, because I don't think it's strange, because if you look at the rest of the construction industry, where they do temporary works, none of that happens for some enormous pieces of temporary works. We don't involve local authorities in that. Some of the concrete frame structures that go up.
Actually around them, I mean, it's a sort of it is purely a temporary installation issue, whereas these are temporary structures that hold people.
Well, you could have 200 or 300 people working on a building site, or the Shard. How many people work in the Shard at any one time? You've got temporary structure, temporary support, temporary things going on there that aren't checked in the same way. If the Shard came down, it caused far more damage than. So it's not that. It may well be for historical reasons, and the fact that it's connected to entertainment, and the licence is about entertainment events. It may well be that that's the way it's been regulated. But that isn't our approach to dealing with these particular with industry in general. That isn't how we do it.
We've reached the point where we're
all hungry.
Got to the lunch break. I've put the lunch off for 20 minutes. I didn't put it off anymore.
I'm happy to answer any other questions over lunch.
Yeah, I'm sure you'll get your earbags. But I really want to express mine, and I'm sure your appreciation for both Gavin and Steve coming all the way up here today to give us the benefit of their experience. And having Gavin here has been absolutely fantastic. So thank you very much, Gavin. We have an hour for lunch and then we're back on with it.
Sort of talks. And by all means, please interrupt me if you want to ask any questions straight away. So treat me as a proper professor and I'll treat you as proper students. Because I will be asking you questions. Just to keep you awake. It's always good for afternoon sessions after lunch. And you notice from my family name, and as Rudi quite rightly said, it's Pavic. You don't have very many of those around, but I'm trying to become a good Yorkshireman for 20 years now. Totally unsuccessfully, but I'm trying. I will keep trying. Okay, so let's talk about first what I'm going to tell you about. First of all, I want to introduce you to who are we, and our being Full-Scale Dynamics Limited. Look at our tagline: real world solution, real world conditions, real world solutions. You wouldn't expect to have two reals for a university professor, basically, tagline. But this is University of Sheffield spin-off company, which is actually designed, and it was established simply to provide real world solutions for monitoring problems of real life structures. And don't forget, here we are talking about structures. Structures being the key word. Why those structures fall, what do we need to make sure they don't fall, and if they are to fall, let's see what can be done to prevent life loss. So I decided to actually carry my commercial hat as opposed to my academic hat or my management hat, simply because I think this is closest to the problem in hand. There is not much here to research. The technology exists. There's not much here to manage. So I think it's a clear increasing awareness seminar, basically, just to tell you what is available and what you can do. So then I will introduce you to the monitoring technology for full-scale structures. And I'll try to sort of present you with a case for treating monitoring as means of inspection. Because when Rudi gave me my homework, he said inspections and monitoring. And I said, well, I'm not really inspector, although I actually started my professional career as a bridge inspector. And I worked for 1 year as a bridge inspector, so I've seen all sorts of things in reality. But I said, I think it's really much more interesting to actually talk about monitoring. Then I looked at ISTRAC-T 2007 guidance, and actually they are explicitly mentioning these two types of loads, wind and crowd dynamic loading, as pretty important, most important ones for temporary stands. So I said, okay, let me show you what can be done with these two types of loading, actually, in reality. And then I will do that by presenting you with examples. This company, and it has 3 directors, and between us, we've done more than 200 tests of real-life structures around the world in the last 25 years. Yeah. So, plenty of experience. We have the largest database of dynamic test results of real-life grandstands in the world, and of real-life floors in the world. Nobody tested many, more than us. And we also participated in code developments, and as you will see. So, I will just show you examples, and then you try to see if anything of the technology can be actually used for your problems. And finally, I'll present some conclusions. So, who are we? It's a University of Sheffield spin-off company. It stemmed from something which I set up myself as a PhD student in 1993 here in Sheffield, which is the vibration engineering section, which is sort of academic research, arm of this activity. Literally started from scratch. There was not a single accelerometer, not a single wire when I came here in 1993. And in 2008, let's say, we had 16 researchers. I mean, it's the same as in 2011 and 12. 16 researchers, 4 academics, and approximately 1 million annual turnover in terms of research income. And we are key, I think in all my modesty again, UK group for vibration serviceability and dynamic testing of large as-built structures. And my idea when I came here was very simple. I wanted to actually, because my background is concrete engineer, designer of concrete structures, concrete bridges, statics, box standard stuff. And it was a very simple idea, and that was, let's get out of laboratories and let's make one step further, and let's see how real-life structures actually perform relative to how they are designed. And if you look at across whole of the civil engineering sector, civil structure engineering sector, that is very often a link which is missing. And simply, last 20 years I spent, plugging that hole and trying to compare real-life performance with design. And we basically discovered all sorts of things that you would never think about. So what is the expertise? Vibration serviceability. If structures are vibrating too much. I don't know if you noticed last night when we had a dinner at that floor over there, how bouncy it was. It was a very, very bouncy floor. That's a classical example of vibration serviceability failure. I don't need to measure it. I'm telling you, it's not good. But yeah, I'm a living and walking and breathing accelerometer. I can even tell you how much G's it has, but I won't. I don't want to show off.
Have you told the hotel?
No, I'll need to have a chat with the manager, actually. Thanks for inviting me, by the way. So, yeah, vibration serviceability, if structures are vibrating a lot, that's basically footbridges, floors, staircases, grandstands, high-rise buildings on the wind loading, towers and the rest of it. Then also we have expertise in structural health monitoring and performance assessment, which is something that, which is basically the crux of the technology which I want to present this afternoon. And also dynamic testing of full-scale structures. When I say dynamic testing, that actually means everything, from strain gauges to load cells to accelerations, you name it, it can be measured. Dynamic simply because I don't believe in statics. Nothing is static. Do you know that we all move up and down 3 microns every 7 seconds? You know why? Because that's the period of the first model vibration of Earth. Okay? Which has natural frequency of 0.14 Hertz. Earth, as a dynamic system, which has mass and stiffness, vibrates all the time. It gets excited. It's excited. The energy stays within Earth simply because we are surrounded by empty space. So, and it's constantly being shuffled. And we all move up and down 3 microns every 7 seconds. So there's no statics. We all move. So that was a research tool as well for you know, to support our academic careers, and that's it. We also try to use those real-life measurements to actually feed back into design codes, and you will see we actually helped. You know, I'm basically sitting on every single, you know, panel dealing with crowd dynamic loading and vibration disability in this country and internationally. And our motto, my motto from day one in Sheffield was every real structure is my laboratory, is a potential laboratory, and it is. Because they're special, they're unique. You know, whenever you build something in civil structure engineering, it's unique. You're not producing gadgets and widgets in millions. Every single design is a prototype. It's a niche area. Not very many people do these things because simply there's not enough work. But when you plug yourself in, then it's quite nice. So this is basically some of our worldwide laboratories done over the last 20 years. Lots of stuff. Pay attention to this one, 260-meter tall plaza in Singapore. We will mention it. About this one as well, you know, high-rise chimneys and the wind loading. So if you organize a bit, you know, all these things that we got involved in reality, we can actually divide them into sort of three categories. One are sort of structures which are excited and dynamically excited by humans, used and dynamically excited by humans. Grandstands, you know, footbridges. The other one are various types of floors in buildings, hospital floors, you know, office floors, and ultra-sensitive floors. This is this is basically a diamond synchrotron next to Rutherford Appleton Laboratory. Did you know that actually, you know, it's a big microscope which works at atomic level, and they're sort of firing little particles, and it's used for material science research. So each of these beams firing particles produces one PhD in 14 days. Okay? And the precision with which the particle actually needs to hit the target, which is about 15-20 meters away, is the same as precision to hit a 10-pence coin with a gun at a distance of 26 kilometers. Okay? So that gives you an idea of what kind of precision is required, just to make sure that the nozzle, you know, from where the particle flies out, and the target do not actually move relative to each other. And these 7 micro movements of the whole Earth is fine, because everything moves together. The key problem is, you know, if there is relative movement. So we can measure that kind of motion with that kind of precision. And hence, you know, this slab on which the whole thing is sort of founded is 1.5 meters thick. It's a concrete slab. And finally, tall buildings or, you know, structures under wind loading is another sort of big area of expertise. Commercial applications of our work, just tell you what we got involved so far. So we were entrusted to organize and execute politically and commercially sensitive dynamic testing of, and now you will see why politically. The Millennium Bridge. We tested it. I've spent there 10 days to verify the solution. Gatwick Air Bridge, longest air bridge in the world at Gatwick Airport. This is the new Wembley Stadium. The Diamond Synchrotron project, as I mentioned, and the Orion project as well. So which is the biggest and the most powerful laser in the world. Again, the issue is precision. So we helped define, you know, a few codes of practice. You know, post-tension vibration disability of post-tension floors, Appendix G of the Concrete Society Guide. I wrote it with Mike Wilford from Arup. And then another version of that is published here, and then another version done by the SCI after that. Then dynamic performance requirements for permanent grandstands. Know the word permanent, it's important to distinguish from temporary. But in essence, it's the same. But we were adamant, I mean the whole working group was adamant that we will deal with grandstands from as permanent structures. And then dynamic testing of grandstands, because did you know that this country is the only country in the world which requires dynamic testing of real-life grandstands after they're built, if they're new, and if they are old and existing. If you want to change usage from sports events to concerts, you have to dynamically test it. Simply because the working group didn't believe engineering ability to predict dynamic performance, because grandstands are complex structures. And it was a huge problem when it was launched in 2002, because consultants clearly were not particularly happy with that. I still went through, which is the reason why, this country has the largest database of, real-life grandstand results. And then also wind coding in Singapore, let's say, that's a colleague of mine, James Grounjon, who is a fellow director developer. So, regarding the technology, this is probably the most complex theoretical, slide that you will have. The main idea, really, about the whole technology which is used is that your structures are actually systems. Let's treat them as a linear system. This is a linear system. I push it here, and it does something here, and then in between, forces are transmitted and whatever. Well, the same thing is with structures. If a wind blows, that's the input. The structure does various things at various points. Produces reactions, moves, accelerates, whatever. That's the response. So that's basically linear dynamic system is the structure. Input is wind, humans, my finger, whatever, and output is, strains, stresses, reaction forces, accelerations, displacements, you name it. Now, 90% of you, maybe 99% of you, are aware of the theoretical route which we take, which is basically what Rudi's software actually does, and everybody else knows about this, which is basically, the route is that you define, if you start from something which is called spatial properties of the structure, which is mass stiffness and damping, and when you define the little elements and connectivities and everything else, you are actually forming mass stiffness and damping matrices. Whichever software you do, whatever you do, it's always this, you assume that. Then you calculate, let's say, in a dynamic sense, natural frequencies, natural shapes, and you assume a certain level of damping. Then you can calculate responses, acceleration, displacements, whatever, at any point on the structure. However, there is opposite route as well, which is experimental route. You may have an existing structure. If you measure responses of that structure at various points, you can actually work out then if it's its spatial properties. Its modal properties, as we call them first, natural frequencies, modal shapes, and damping, and then also its mass stiffness and damping matrices. It's called inverse analysis, and this is what we do all the time. All that you need is a structure and a few transducers, and actually huge amount of ability to actually do this step and do this step. It's possible. It's done all the time. So the whole concept is actually based on this. And if actually both routes are producing the same set of consistent results, then you are happy that your prediction, your way how you're predicting actually makes sense, because you're measuring and you're able to go back. So what is our approach to full-scale structural performance problems? First of all, always do analytical modeling, even at the back of the envelope. I mean, if you use mathematical formula, you're doing analytical modeling. Typically, we use finite element analysis, usually ANSYS software, but you can do other things. And then we also do simulations in other pieces of software like MATLAB. So some kind of analysis is done. We also do dynamic testing, or some kind of testing of the structure. It's called model testing rather than model testing, using shaker excitation, using natural environment excitation like wind or microtremors or whatever. And then we do measurement, vibration response measurements. Or we can also do remote monitoring. We have a number of structures, as you will see later, which are permanently instrumented 24/7, and data actually feeds here to the server in Sheffield, and the client can actually go to the web page, protected web page, and see precisely what his structure is doing at every moment in time. And obviously, the key skill is to make sense of these two things and make sure that they talk to each other. There is a whole technology developed in mechanical and aerospace engineering disciplines called FE model updating, correlation, and by doing these two things, sort of interactively, the whole aim is actually to learn how to model better dynamics of civil engineering structures. Let's say under human loads, but it can be also under wind loads. So we do take advantage of latest developments, and I always advise, you know, see what is there. What I'm presenting you today with is what literally is available worldwide only in the last 5 years, maybe even 3 years. If you asked me 10 years ago, can you do that? Would I be able to do what I'm showing you today? No. The answer would be no. So it's really hot, hot from the press. So this is that ultra-sensitive, you know, accelerometer or velocimeter, which we use for, you know, measurements like synchrotron labs. That technology exists. We also tend to do a lot of you know, field work and data storage. You know, make sure that it's there. We always try to use also absolutely best possible technology, because there is not much point actually cutting corners with the, you know, with the cost. This is how typical, you know, sort of field testing setup of a floor looks like. You know, test crew is always minimum 2. Usually we take 6 people with us, and this is typical, you know, long-term monitoring, you know, kit. So if you want to do long-term monitoring of your marquee, long-term could be a week, or 2 weeks, or 3 weeks. This is all what you need. You don't need anything more than this. This is actually 10 channels acquiring data from a chimney.
Do you need a different set of equipment for each structure, or do you need one set of equipment for several structures?
That's a very good question. And everything depends on how long you tell it. You know, it always goes, you will see a slide later, it needs to go with the structural engineer, who needs to advise, you know, what kind of parameter needs measuring. Strains, stresses, forces, reactions, accelerations, displacements, depending on the structure. I mean, you can really have weird and wonderful, you know, structural forms in this business, and therefore it depends on what the structural engineer advises. I'm pretty confident, and I can assure you, whatever needs measuring can be measured. The technology, again, 10 years ago I wouldn't be able to do that. But now the technology is there that, you know, if you need displacement at a particular location, measure accelerations, integrate twice, you get it, you know, dynamic displacement and wind loading. It's not a problem. Strain gauges as well, you know, strains, it is not a problem. Typically, the way how I see things, now that you ask me, is, you know, my understanding how the industry actually works is that there are, you know, sort of components which are rented and that are, you know, shipped around and, you know, put at various locations. Those components can be actually pre-instrumented, you know, with cables, everything else in place. You put them together, you know, put accelerometers or strain gauges or whatever is needed in place when it's erected, and that's it. Normally, for a normal life, for a normal, let's say, floor with 24 accelerometers, we need between 2 and 3 hours to do the full instrumentation. You know, and on structures like this, you actually don't need very many test points and very many, you know, parameters to measure. Maybe half a dozen. Half a dozen will tell you enough about. And that's a typical misconception. There is a stone cutter's bridge in Hong Kong, and you know, the instrumentation system costs multi-millions. It has 2,000 channels. You know, they measure everything you can imagine. You know, strains in cable, absolutely unbelievable amount of data. The biggest problem is making sense of that data. That data is feeding in, you know, gigabits and gigabits every hour coming in. They don't know what to do with that. That's the key challenge. You know, it's much better to have 6 well-placed, reliable transducers somewhere on the structure, and based on the advice of the structural engineer, know precisely what you're going to do with the data from there. And that's it. You don't need more. These are, you know, we are not concerned about local failures. We are concerned about global failure of the whole thing, you know, falling down. And that means that you need to measure global property of the structure rather than, you know, local parameter. This is basically, we developed this completely customizable, you know, depending on what the client wants. But there are 3 lines here. This is used on a chimney. I'll mention this later. You see, there are 3 levels here. This is basically be worried. This one is be very worried. And this one is run away. You know, to put it simply. In 3 years, there was only one time when it was here, actually. And you will see which structure is in question. I can mention the names, it's no problem. It doesn't exist anymore because of this matter. So we also have, and we are the first ones in the world to actually launch technology for automatic data processing. So you don't need to download the data and wait for somebody to analyze it and issue reports until that. You literally, the data gets processed all the time, and you get automatic estimations. I mean, in this case, it's estimation of damping level. This is estimation of natural frequencies, and you end up with a report like this. This is a typical 24-hour report. I think it's every half an hour producing set of natural frequencies and damping values for a particular. It was a chimney in this case. And this is a typical data acquisition system, instantaneous monitor, and then post-processing, instantaneous post-processing, and reporting every day at the end of the day. Let's say what happened with that structure. It can be reported every half an hour if you want. SMSs, emails. It's completely customizable in that sense. And then also this one is interesting. I'm going to show you actually what this thing actually here does. This is basically Singapore Republic Plaza in Singapore. Is this building here I mentioned? I told you that I'm going to show you something. It was instrumented at 5 levels. And Singapore is not far away from Aceh, and you remember the big earthquake over there and tsunami, which happened. So we were very lucky, actually, to be able to, to actually see what an earthquake can actually does. So, have you seen actually what earthquakes do to a 260-meter tall building? How it actually looks like? If you haven't seen, look at this. This is basically earthquake. Recorded. This is the top. This is the bottom. So that's where we are at the moment. It was a few thousand kilometers away. It was still strong enough. And this is actually, it measured accelerations. If you integrate accelerations twice, you'll get displacement, basically. And that's actually what the structure does during the earthquake. The whole thing just moves, everywhere. And actually, you can get this kind of visualization for, let's say, during events, during, I don't know, high winds. And just instrument it straight away and see precisely what's going on with the structure. It's not a problem. We do that all the time.
Sorry, Alex. So what you're saying is that we would be able to have a laptop screen and get this kind of visualization of the main stage at a music festival or a concert at Don Valley Stadium here.
Yes. Last night when I saw that video, that showed it, the first video, I thought that if that was instrumented properly.
You heard about the Indiana?
Yes, the Indiana collapse. I don't think that there would have been always enough warning, because these things always get. If you define 3 levels, be worried, be very worried, run away. There is no way with a system which is reliable and you can actually build in redundancy the rest of it, that you wouldn't be able to pick up if something fun is happening, and you would definitely have enough time for people to run away. That's the whole point. You mentioned a few guys with to tighten ropes and guides or whatever. I think this would be actually more reliable solution than that, because they need to be told that something is going on. Whereas in this case, basically, you have system which don't forget, these systems are used now to monitor 24/7 absolutely major objects of infrastructure. Stonecutters Bridge, Humber Bridge, Tamer Bridge in Plymouth, and the rest of it. So there is now with this level of technology, they are sufficiently reliable. You can actually do that, and it's not costing Earth. Compared to 20 years ago when I started doing this, I think prices are probably order of magnitude lower for a system to set up and pick up. It's just It's, and which is why, you know, I think this seminar and awareness is very important. So, yes?
You say it's not a great cost.
No.
Give us a certain ballpark figure of what 6 of your attendees is in equipment cost.
Depending which one do you want, and you know what kind of what Alan basically tells, what the structural engineer, you know, tells you. We are talking about £200 a transducer, you know. If you want, because for this kind of levels of the vibration and everything else, you can go for a piezoelectric accelerometer, 100 millivolts per G sensitivity, typical mechanical engineering applications. You're not after ultra-sensitive kind of things, which tend to be very expensive. Data acquisition laptop is £500, a bit of cabling. So probably for 5K, you can set up a system. The problem is that the development is the problem. So if you know, to develop something which is reliable, working 24/7, etc., that's what costs the money. But you know, something that is reasonably reliable, you know, 5 to 10K of hardware is you know, more than enough, basically. And the way how I envisage it, you know, cables are there, everything is there, put together. Somebody goes there, puts accelerometers and or any other transducer which is required. You know, cherry picker. I've done instrumentation of one post, you know, from a cherry picker, 15 meters up, no problem. You know, everything goes down, plug it. I was told not to rely on mobile phones around big venues because of, you know, masts tend to be saturated with, you know, phone calls and things like that. But it can be done locally, so it works.
So could this not be fitted to, for example, a stage roof that is critical, with 50,000 people stood in front of it on a permanent basis?
Absolutely.
And move with the stage?
Yeah.
So you don't need to do it every time you move, you do it once and then you have monitoring.
Yes. Yes, I mean, the only problem is that depending how rough the conditions are, because these, you know, LS accelerometers, they tend to be a bit sensitive. You know, if you want to measure fraction of a G acceleration, you need to be careful what you're doing. So the only complication which I envisage is if handling of those things is rough, you know, people are throwing them away, or I don't know how it works.
And you could, well, that is a problem in the industry, use and abuse. So you could remove these
absolutely
measuring tabs, but have them tree-wired and just slot them in.
Absolutely, yes. I would go with wireless. That technology still doesn't exist, although people will, you know, salesmen will tell you it works. I'm telling you it doesn't work. Forget it, basically, for the next 10 years. You ain't gonna get anything with wireless. I know that because we're testing constantly, you know, the best possible solutions which are available. We know who the key players are. We always get the stuff from them because we are now being asked to try things on behalf of equipment developers because they know what kind of stuff we do. I mean, we can do any kind of dynamic testing ever described in literature in English. You know, that's not a problem. The problem is to have basically wires placed, which is the complication, time-consuming exercise. It's fixed, placed, secured, and then when the whole thing is put together, somebody goes with a cherry picker or whatever, just, you know, screws in an accelerometer or, you know, glues a strain gauge, and things get connected down, you know, somewhere at the backstage, and that's it. I have a system. It's working. Okay. So what are the client's benefits, actually? I was thinking about this sort of in industry. Client's benefits is, does the temporary product, let's call it a temporary product, do what it says on the packaging, i.e. what the structural engineer says how it should perform? Does it meet design specifications under various conditions? And you will see that these sort of wind-related products are always coupled with wind data. So you can monitor wind data literally instantaneously, know precisely direction and speed, and then correlate that with what the structure does under that direction and speed straight away. That's precisely what you know, chimney people are interested in. We develop the technology; it's available. Reduced probability for sudden and unannounced collapse. I would say actually considerably reduced probability. You will know if something is going outside predicted envelopes. Same with airplanes. You know, all of them, for the shape of wings and everything else, have defined stall speeds. If you're approaching stall speeds, it will start buzzing in the cockpit. Well, that's the same thing can be done here. You know, if particular displacement or acceleration is, you know, reaching critical levels, then you will know it straight away. And you will have more confidence in, sorry, this is in rather than is, structural performance over many sites, because you are, if you are moving from one site to another, you are actually building a new structure every time. You know, they're not the same structures. As soon as boundary conditions are changed, it's a different structure by definition. So there you are. And I would say that actually has the potential to reduce insurance premiums. We are now discussing this whole technology with insurance companies, trying to actually, because we are talking about, you know, objects of infrastructure which are multi-billion-pound worth, and there is, I think, appetite to actually use this statistical data from response measurements and the various conditions to actually see what the structure actually does. So let's see which technology is actually available for full-scale temporary demountable structures. I mean, you all know this, what various types of structures are: grandstands, marquees, stage, various types of stage structures, towers, masts. What are the specifics? They're required at short notice. Fine, it's not a problem. Typical significant loads are winds and crowds. Fine, not a problem. We can deal with that. And another specific is structural components are lightweight. It's not a problem. Rapidly assembled. Fine. Readily dismantled. Yes. Reusable. Yes. So nothing of these specific things make the technology which I'm going to show you not applicable to, you know, your application. Temporary demountable structures, that's basically the cover page from the 2007 guide, as you well know. And actually I read it twice. And what I found, my conclusion is everything is in, actually. It seems, and from the discussion this morning, it seems that the biggest problem is what is written is not being applied in practice. Well, if that is the problem, then actually having systems like these, you know, monitoring system, can actually to some extent alleviate the problem. Because, you know, you will know if the structure is performing or not. It's all about performance. And you will know if suddenly you get, you know, too big accelerations or too low, you know, sort of force at a particular, you know, anchor, which again can be measured, then you will know that something is, you know, something is not as it should be. So you can take immediate, you know, remedial action straight away. And being, again, don't forget, I was a, you know, bridge inspector for, you know, for some time. I saw the technology used for that, which is basically, you know, a digital camera and, you know, your eyes. That's a technology. It's nothing else. You know, just to see if it makes sense. This is more reliable. What I'm selling.
Alex, sorry to interrupt again, but it seems to me, and I'm trying to refer back to previous sessions, that one of the biggest issues that Tim raised, for example, was who made the decision to cancel an event when there are so many commercial pressures on the safety officers. And this is the kind of tool that would help them make those decisions.
Exactly. I'll give you a very timely example as well. Another type of structure. You heard about the chaos caused by Hammersmith flyover just before Christmas in London, when they closed it suddenly. Okay. Well, there is a theory it was unnecessary to close. And the flyover was monitored, and it was monitored with acoustic emission technology. Acoustic emission technology gives you information because it's made of, you know, pre-stressed concrete. There are wires going into, you know, through the pre-stressed beams, and the bridge was instrumented since summer 2010, and in November, December 2011, they noticed that acoustic emission technology was indicating breakages of significantly higher number of pre-stressed wires than normal. And on the basis of that, they said, okay, right, we need to close everything. despite the fact that actually the bridge was inspected and partially closed practically throughout, for quite a long time, throughout 2010 and 2011. But, they made risk assessment, and on that basis, they decided to, close it finally. Now, there are two theories. One is it was not necessary to close it. I don't know. I don't have enough information. Another theory is that they did not close it until they really had to close it, because they were confident that everything was fine until that particular moment. So this tool can actually give you probably more confidence that things are fine than otherwise. Because don't forget, you will get information from the structural engineer about wind speeds. I don't know, 26 meters per second, whatever. Is this 24, 26 when you need to take some action? That information is reliable only if the structure actually does what it says on the tin. And that's the crucial piece of information which you don't have. It's all fine. 26 meters work fine on Alan's models. But does it work fine in reality? You never know, because you don't know what the structure is doing actually. If all those forces are where they should be, if all those weights and masses are as predicted in the model. The technology actually gives you the way forward, because that's the missing link, to actually link analysis with actual performance. And quite often analysis is based on conservative assumptions and the rest of it. I'm not saying don't evacuate, but I'm saying maybe you need to evacuate even earlier. Not at 26, maybe at 22, if something was wrong with the structure. It just gives you that, for not a lot of additional money, it gives you additional level of confidence. So let me show you what can be done these days with wind loading. Let's try to distinguish between two things. One is health, the other one is performance. On the left-hand side, we see two examples of systems, like a human and a car, where clearly health is a problem, or could be a problem. In this lady because of her age, you would expect naturally, and this car maybe because of the type who made it, reliability or whatever. But clearly that is an issue. On the right-hand side, we see a healthy individual and a pretty good car, and reliable car, let's say, in theory. So we are really not concerned about health, we are concerned about performance. Does it do what it should do? Does it really accelerate between 0 and 8.2 in 8.2 seconds to 60 miles per hour, for example? In structural engineering, we can also have similar way of thinking. In this case, health is a problem with structures. In this case here, it's the performance which is an issue. So actually, what you can do when you are monitoring things, you can actually track performance and pick up problems with health when they occur. There is a concept now that with civil structural engineering, by the way, our profession is the only profession which produces prototypes all the time. Unique structures. Every structure that we do is unique, as opposed to cars or aeroplanes or other widgets made in millions. So when you have, if you have structural health monitoring requirement, then these are the things that you can do. You can evaluate performance against specifications and standards. You can track, which means time, repeated things, and characterize structural loads, overloads, and extreme responses. Extreme winds, extreme, rain, extreme, crowd loading, whatever. Evaluate structural performance and safety during construction. That's more for, more permanent structures, let's say. Check novel systems of construction and structural forms, if they really do what they are supposed to do, if your analysis of assumptions are correct. Validate structural modifications and mitigation measures, you can do that as well. And provide feedback loop to design and loading codes. So you basically learn what the structure does and say, You know, this is how it should be designed. All these elements are called diagnosis. Basically, it's like a medical term. You know, we are doing some kind of diagnosis. However, if you can then use structural health monitoring to do the following as well. Assess structural viability after trauma, for example, after earthquake, impact, bridge scar, whatever. You know, you can actually see if the structure is viable after that or not. Track long-term degradation to aid maintenance decisions. For example, repeated, you know, usage of a temporary stand. Does every time when you put it together actually does the same thing, or is it deteriorating over time? Detect damage. That's damage, and I put it on the quotes. In the case of temporary structures, damage may be loosening of anchors, for example. You know, changed boundary conditions. In that sense, you know, changing forces in cables. And also provide warning of impending failure. And all these four aspects are actually prognosis. So these are, you know, first let's see what the problem is, and then let's see what the structure, what we can expect actually the structure is going to do. Now, typical elements of a structural health monitoring system in civil engineering, which is applicable to temporary ground stands, is this. You need sensors, static or dynamic sensors, local data storage, processing, data transmission. Then you do system identification, which is basically to find, you know, properties of the system, some kind of manipulation with the data. And as you can see, this is all based on, you know, literally data from which you're acquiring constantly from the structure. And this is all these steps here lead to the creation of something which we call, in practice, data-driven model. Offline, you can do finite element model, which is basically what you know, software does. You can do also, you know, dynamic testing results, one-off, you know, check natural frequencies of things. And you can do also a comparison between FE modeling and dynamic testing just to see if they make sense. Then you can actually link data-driven model with this sort of offline assessment, and then you can, when you have all of the information about what your physical model is doing and what your data-driven model is doing, which is basically, you know, time histories of what you're measuring, you can link them into a process which is called anomaly detection. And you can actually, based on anomaly detection, you can actually issue reports, alerts, decisions, and the rest of it. Now, this anomaly detection is a funny new area in structural health monitoring, and it's really based on training the system to understand when something odd is happening. And it can be done. The technology exists. The system is simply trained to recognize what is normal for a particular set of information, and you need, you know, longer term data, and then, you know, suddenly if something happens, it will pick it up and it will tell you. Aerospace engineers do this all the time on airframes. These are very well known examples of these structural health monitoring systems installed on real life structures. Hong Kong, there is a bridge in Greece, tallest building in the world. By the way, our system was shortlisted for this. So it was one of the two shortlisted, but we didn't get a contract. And also Guangzhou TV Tower in China. So, you know, people are using this technology for permanent structures. Now, can this whole thing work for you? Right. I'll tell you, you know, this is my sort of honest assessment. So, first of all, the situation currently is that usually the system is implemented for a specific purpose and often for some kind of troubleshooting. So either is a problem, you know, floor is vibrating too much, or something is already noticed that is wrong, then the system is used. I'll show you an example when it was actually used for structural modifications. For most cases, vibration and strain data are enough, and you don't need very complex systems. This is what I'm saying. You know, half a dozen transducers will strategically positioned will solve your problems. Instrumentation is inexpensive. MEMS accelerometers, MEMS means micro accelerometers can be used. National Instruments hardware, a netbook, 3G modem, now which is another reason why it's only available in the last 5 years. So you can actually stream data straight away whenever you want, if you want. So money is not a problem anymore. Weather data is incredibly useful, retrievable from local met stations. You don't need an anemometer, available on the site. And actually, your structure will disrupt wind flows. So you will never be able to measure realistic wind on the site unless you have a pole, specially erected, 200 meters away, etc., which is a lot of cost. What we found is actually, if you use local weather station, and this country is peppered with them everywhere, it's not a problem. Find the nearest one, and it will do. If you try to measure wind on top of your marquee, forget it. It's totally unreliable because marquee itself is disrupting wind flows and you're getting unreliable data. I've seen cases where people try to do that and say, oh, on top of our building we put an anemometer. Useless. But, and this is a big but, you see, you have to work with a structural specialist to tailor a system to provide appropriate information in your real time. It's absolutely essential that the person who designed the structure actually informs decision making in terms of what and how to instrument. Installing power and protecting is not so simple, but it can be done. You have to think about that. Make sure that you don't forget your accelerometer attachment when you start dismantling, because otherwise they're going to destroy it. And we have many success stories in using just vibration data without any strains. This is the first story, which is Dubai. It's not done by us, but we know what they've done, and it's quite nice and impressive. This is our structure. It's a Rudi chimney. It's a nice story. Built in 1968. It's a 183-meter high chimney, and we needed to provide, this was the specification, a real-time alert of large amplitude oscillations with potential to cause failure. Precisely what you need for your structures. And guess what was the loading? Wind. That's it. And we also needed to track, that was what the client wanted, performance of vibration mitigation device, which is tune mass damper, which was installed on it, just to make sure it doesn't collapse. Now, you may ask a question, why on earth it wanted to collapse suddenly now, when it was in place since 1968, and I was 5 years old then, so I clearly didn't do any instrumentation in 1968. This is the chimney. I'm trying to explain what is the rationale. So that's the old chimney in the Rudi power station. Very important one. If it doesn't work, then half of Midlands will not have power. And what was happening is that they decided to build a new chimney, downstream from the old chimney, in the direction, this is north, in the southwest direction. And guess what is happening in Rudi at that location? At that location, look at where the predominant winds are coming from. Southwest. Okay? So the key problem was vortex shedding. And this simulation here actually shows you quite nicely, what this is the new chimney, this is the old chimney, and this is precisely why we got a contract, what they were concerned. This is nice, fluid dynamics simulation. Look at what the new one is doing. Because of vortices coming off, this is the old one, and look at how much more it moves actually than the new one. So they were clearly worried that this one's going to collapse. And they actually started noticing that some funny things were happening during windy days when they started building the new one. So when they were around, 30, 40 meters, they said, oh, hang on, right. Let's see what's going on. And they commissioned straight away, the monitoring system, and the rest of it. And not only the monitoring system, they also commissioned this thing here. Sorry, you will see what the tunas damper, which was put on top of the chimney just to reduce the level of vibrations. But this was a standard example of the technology, which I think can be used here. Structural engineer did analysis, and they basically said, right, up to this level here, you're fine. If accelerations are up to this level, you're fine. If you are here, then this is basically higher alert, and this is basically imminent collapse. As simple as that, And there's not much, this is linear scale here, so there's not much space. Twice higher responses, and it's collapsing, basically. Factor of safety 2 makes sense. It's not far away. Everything makes sense. And this was literally the whole of the system. Signal conditioning boxes, a little bit of, this is literally BT modem, you can buy it for 30 quid now. Laptop PC, and that's it. That's all what you need. And a couple of accelerometers at the top. There was, then later on they asked us to do a bit more. So there was a couple of accelerometers at the top, and then they wanted some lower accelerometers as well later on. They commissioned the tunemass damper, and tunemass dampers, it was, by the way, it was the largest, as this thing here. It was 40 ton of steel going around the chimney. And they were very worried if it would perform. Because one of the problems with tunemass dampers is they really need to get engaged. If they don't get engaged, then and they sort of start moving together with the structure, then they're not working, and then it's even worse. Because you have 40 tons of dead steel at the top of the chimney. It's even worse. So they wanted us to actually monitor damping in real time, processing data straight away, and to tell them precisely if it was working under large wind conditions. And look at this. This is this was on 29th of February was the windiest day, which we recorded. Baseline damping, when the damper doesn't get engaged, is because it's sticking, is 0.7% of the whole thing. And then when the wind started blowing, look at these two values here. Damping actually started picking up. The values are now much higher in terms of amplitude, and we were, damping went up to 4%. So perfect. They had their proof. But the trick is they needed instantaneous decision. First of all, we couldn't put somebody to look at it 24/7 non-stop, which means we need to have a system whereby it will pick up, strong wind straight away, check what the damper is doing straight away, and inform them that if the responses are too high and the damper is not producing necessary damping, they need to run away, basically. Which will be seen both from the damping value and from the levels of overall response.
So could this be comparable to, for example, a live lighting and trussing system suspended from the roof of a stage roof?
In what sense?
Well, because it's suspended on cables, it can move.
Yes.
And if it moves in the wrong frequency, it can affect the stability of the roof.
Well, I would, in that case, depending what is the remedial measure to change the frequency of the suspended system.
I was just thinking about warnings.
Yeah. I think you always need to focus on what is carrying what. You have to think about the main structure, and which is the roof. So roof needs instrumenting, so that you know what the roof is doing. And then, for example, if the lighting sways too much and is disrupting performance or whatever, then it needs more measuring as well. If it doesn't, then you just forget it, basically. But always think what is most important. However, what is also interesting is that on 306, almost a year after, you see how many days, this is all measured on a day-by-day basis, 12 times a day, all these points here. And then suddenly, 350, 60, 70 days after the beginning of measurements, we noticed absolutely colossal drop in the natural frequency of the chimney. And that was clearly picked up by the system. We are talking about 0.34 dropping to 0.24, because natural frequencies go with the square root of stiffness. and assuming that the mass was the same, that indicates 20% loss in natural frequency would yield straight away that's 1.44-50% loss in stiffness. So that means crack is maybe opening somewhere, and there was a potential for imminent failure. So they immediately, everybody, about 10 engineers started working on this, trying to see what was going on. First, of course, asking us, did you make a mistake? Maybe it's a measurement mistake. It wasn't a measurement mistake. And we looked at the stuff, and actually what they discovered is that, chimneys usually have a liner, inside liner, which is actually protecting the outside from high temperatures. And because they, these liners, they tend to be sort of filled with dust, and they expand, they shrink on varying temperatures and the rest of it. And we actually picked up the case when that liner, because they started cooling down the whole thing, it wasn't working sort of every day anymore. The regime was changing for the chimney. And one of those days that, it just didn't click. And at least that's their explanation. So they thought it was safe enough, and eventually this is what happened with the chimney. We monitor natural frequency between day 926, since we started monitoring, and 941, 942. And obviously, as they were dismantling it, and the frequency was going up because the chimney was becoming shorter and shorter. And this was recorded with an accelerometer at the bottom. So it was doing precisely what it should do for its length on every single day. So they were very happy. They were not disrupting anything new, so that sudden collapse may happen. So that was the last good thing. The chimney doesn't exist anymore. I won't bother you with precise conclusions, but I hope I convinced you that a system like this could actually be quite useful for your applications. This is a Tamer bridge, structural health monitoring system. Again, long span bridges, we use them quite a lot. They are quite interesting because of their major objects of infrastructure, and it's very important that they function properly. I will skip through these slides because it's again very similar application to the chimney. Wind was the assumed loading, but then eventually what happened and what we found. By the way, this is a slide which actually shows variety of transducers you can actually put in. For example, you can put in anemometer on your structure. Bridges are different. On bridges you can put anemometers at the top, so they're not big and bulky. Temperature sensors, very useful as well, in particular for slackening of cables and checking forces. So we put that as well. Strain gauges are here to measure forces. You measure force typically by measuring strain. Although there are piezoelectric force cells you can use as well. So you can put variety of things. On this bridge, I think the system is quite complex. And this is a typical this is what we have on site, and then the data gets transmitted to Sheffield, and then from Sheffield, actually the client logs in through a web server, and they can actually see precisely what's going on in every day. Now, this is a web viewer, by the way, so you can see precisely what the bridge was doing at any particular time. In this particular thing here, we have temperature gauge on a cable on one of the stays, and we also have force measured in the cables. So as you can see, as temperature varies every day, because of day and night variations. And then it's interesting on the February the 6th. Now this is my question for you. Look at this data here. Let's see if you can actually make sense of this. On the February the 6th, as you can see, and a few days before and after that, it was pretty flat. What does that mean? Temperature-wise? Yes. When does it happen? Sorry, cold? Well, when it's cold, it goes up and down. Overcast. Yes, if you don't have lots of sunshine, This is what is happening, in particular in this country. Okay. Now, you would expect, as you can see here, you know, all of these variations were always accompanied with changes in forces in cables, which is normal, because, you know, slackening, tensioning, stuff. During this overcast period, you would expect that the cables are pretty much flat. And indeed, look at this one. Flat, 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 not so flat, and not so flat. So immediately they picked up and said, ah, hang on, something is happening here. And what was happening is that we found that, you know, what was found is that as opposed to, they were always thinking that wind is the biggest problem with, you know, this bridge. Because at one point in time when it was built, it was the largest one in the UK, in the world actually, of that type of structure. But actually, the key driver of dynamic response of the bridge are actually vehicles on the bridge, rather than wind. And this variation here happened in some of the cables because of overloading of one side of the bridge during you know, rush hour. And that was picked up from the system. I'll show you where the system is. From this, because all our systems, by the way, come, if you want, with webcams. So you can constantly correlate, you know, if you see a tide, you can see time, you can see night, and you can see, you know, where the cars are, and you can always correlate what is actually happening in and out around your structure with what the structure actually does. And this is toll data, because Tamar Bridge is a toll bridge, over 1 year. And you can see that you have quite a lot of you know, mass on the bridge. This shows the amount of mass on the bridge, and this is hour per day. Mass increases during rush hour, 7, 8 o'clock in the morning, and then increases in the evening as well when people are going back home. And then we managed actually to simulate the whole performance using finite element model with precise loading of bridges with, you know, cars and everything else. And look at how good the simulations are. You know, around, you know, in the morning you're getting drop in natural frequency because of more mass, and in the evening as well. Okay. By the way, we also, you know, this was a very interesting test. They moved 200 plus ton heavy generator component across the bridge, and the bridge was instrumented. And actually, with our technology, we were able to see precisely, oops, I do apologize. Let's see, this should work. We were able to simulate precisely what was going on with the deflection of the bridge during the transport. And it was pretty, you know, accurate from both analysis and measurement point of view. This is experimental data. You know precisely, you know, what the deflection is just by integrating information from the transducers. Regarding crowd dynamic loading, I'll try to be quick here. As I gave you background about the, you know, grandstands and you know, how the problems were created. The biggest problem with grandstands actually occurred late 90s, you know, 2000, when they built when the Cardiff Millennium Stadium was built. And Manic Street Preachers couldn't have their concert, Millennium Concert, because they did a 14-meter long cantilever, and somebody, an inspector from local authority who needed to issue the certificate, just did this at the tip of the cantilever, which is called the heel drop test. And the whole thing was just, you know, vibrating heavily. She said, oh, sorry, but, you know, it's not on. Natural frequency of that system was very low. And it was very embarrassing because it was happening on an absolutely brand new 70 million pound sort of structure. And then there was a number of other cases. Liverpool stand gets a red card because of, you know, bouncing. There were 2 more wobbly stands reported again by Construction News. You know, Old Cricket Ground, I think somewhere in Manchester also. During Robbie Williams' concert started shaking, and then the government set up this working group, which after 8 years produced new guidance, and I start there. Just to show you why you should never, ever, ever be complacent about what crowd can do to a grandstand. Watch this video and imagine something like this happening on a temporary grandstand. Look at the level of coordination which they achieve. Forces are absolutely colossal. If your structure is not proper structure, if they start doing this and you are not managing them, it will collapse. Eventually, they put two nose dampers, behind this one, but it's a permanent stand. The natural frequency of this system is 2.7 Hz, which is why they were able to excite it so easily. I'll show you another one. I mean, Bruce Springsteen is known to, his song "Twist and Shout" is known to have destroyed foundations of Gothenburg Stadium. Cars were parked like this before the concert. After the concert, they were all skewed like this because the fans actually created a mini earthquake. So this is him basically, receiving the award and sort of explaining what was going on. And this is actually what the fans actually did during the concert. I don't know, I lost sound on this one, but you remember Twist and Shout and what he does? Look at what he does. Look at it. And literally, causing a mini earthquake. This is all will slow down. And the level of coordination is absolutely amazing. And that means that, if they're exciting resonance or, imparting forces, it's huge. If I do this, I'm 80 kilos. If I do this, the peak force created here is 300 newtons. Okay, it's 300 kilos. It's just, sorry, 3 kilonewtons, I do apologize. Just by doing this. So, and then if I do this, it goes up to 5 kilonewtons. I'm talking about peak force. It's static versus dynamic. Let me just finish off this. This is basically showing the technology and the rest of it which you can have, but to test the stand, and this is the technology which you can use actually to measure global motion, because these temporary grandstands tend to sort of have difficulties with global stability, sort of swaying. You can actually measure now quite nicely. See these sort of global modes of vibration. See if they are where they should be according to the predictions before you start loading them with people. That's not the problem. The structure exists. We tried this technology for monitoring of real life structures. And we monitored Manchester City Stadium for over a year. Lovely project. I mean, it's one of the best things which we've ever done. And why do you want to obviously monitor? Just to show you that these sort of coordinated fans don't happen by chance. These are, I have Turkish fans. They're also quite good. But I think these are Germans again. Now look at what they've done and what they do. If you don't have management strategy to actually prevent them from doing this, it's literally just stopping, getting stewards involved and stopping. You really have to think twice, if you want to allow this kind of stuff to happen. This is a very sturdy and stiff structure, and as opposed to temporary structures. But now look at what's going to happen when they. You can imagine, you don't need a lot of imagination to sort of imagine what would happen if something like this is done on a temporary stand. Okay, and this is, this was a concert of Red Hot Chili Peppers, during our monitoring of Manchester City, where the accelerations actually during one of their songs went up to 1 meter per second square, which is 10% G. You see, nothing was happening until suddenly they started doing A little bit more coordinated things. But what's interesting is that this is all they've done. This was the highest ever recorded in 1 year, response. And okay, they are coordinated. They do a bit. This is it's a 4 meter long cantilever, but they don't do much in order to cause 10% G, 50% G accelerations on a very, very sturdy, stiff structure, permanent grandstand. So, Crowder's dynamic exciters are very, very nasty. And always think twice before you let crowd do anything like coordinated activity on a temporary structure. Okay. Okay, so we have the technology, by the way, where we can actually build models, do testing, and then verify. This is basically, the red dots are, test results. The blue lines are models, and you can see that the two things actually match quite nicely. It's called FE model updating technology, and you learn all sorts of things. So this is my last slide, just to summarize. I went quicker through the crowd dynamic loading because I hope you believed me after you saw what we did on a chimney, that similar technology can be done on something which is much more down to earth. And you can actually monitor what the structures are doing. We can do assessment of a real life thing. So I hope I convinced you that the technology exists, that you can actually measure instantaneous responses and produce warnings as things happen, literally instantaneously. Technology also exists for long-term performance tracking of things which are either put in place and then left, or assembled and disassembled multiple number of times. For wind loading and for crowd loading is precisely what I showed you. Analysis and monitoring are mutually supportive, and they always need to go together. They must go together. Plan measurements up front, based on the advice of the engineer, and in particular when planning budgets for events. Develop useful specifications for the measurement. Obviously, everything needs to be prepared well in advance, based on the advice of the structural engineer. Engage measurement consultant to help you with it, or basically just have permanent instrumentation on your structure. That service can be provided, and we can train what needs doing and how it can be done. Plan time and space, and plan the costing. You need to be realistic, and think always about who can actually do the work. There are lots of cowboys around, by the way, who will tell you it will work and it may not work. And plan also data flow. This is the key, really. Always think about 2,000 channels on Stockhatter's Bridge, and gigabits of data where nobody knows what to do with it. Learn and have prepared strategies. What are you going to do if you start getting responses which are above certain thresholds? And be prepared to cancel the whole thing if it's needed, straight away. So it may work both ways. It may tell you, okay, cancel it, or it may tell you you don't need to cancel it. So depending, where you are. The technology is reliable, I would say, for the purpose of your usage, and it is used in very many safety critical applications. And on that note, I would like to finish. Thank you very much.
Thanks very much, Professor Pavic. Alex, now our new friend. We're looking for a project to try this on. So if anybody can think of a suitable time, there's no doubt it'll work. And it's my honest belief, and having met Alex and see some of the, he hasn't shown you some of the stuff he's done, he hasn't had time in only an hour. But it's my honest belief that 10 years from now, every major portable structure will have some form of live load measuring. Because to turn around and say that video, and we're going right full circle to the first thing yesterday morning now, where we watched that dreadful video that's almost a snuff film. That made me happened. If we had live load monitoring on it, they'd have got everybody out of the way. Okay, we know there are simpler solutions to bracing and stabilising. But that advance notice, let's go back to Puckle Pop. People running into a tent as it's falling down. One king pole standing up let 1,000 people out. If they'd had 5 minutes advance notice, everybody would have been out. So, Alex has gone into incredible detail. He's an incredibly busy man. I'm not pulling him up in any way. He runs a £40 million a year department, or departments. He's took the trouble and the time to come and spend an hour with us, and I think it's fascinating. I didn't understand it all, I'll be honest with you. I understand quite a bit of it, and I understand about natural frequencies, but I can see that it is the future. I hope you all agree, and I'd like to thank Alex one more time. A lot of things that we were going to do in the last session have already been covered, partly by Steve this morning and Tim, and various other people. So we've got tea break now, which I'm going to suggest we make a quick one. And I'm going to invite Tim to come up on the stage again, who's been quite vocal over, and very successfully so, rather, may I say. And I would like us to think about where we're going to go from here. I think we've learned some conclusions. If you'd all like to think over tea, whether you've got any suggestions of where we go from here and how we implement things that we've learned over the last 2 days. Because we've got half an hour, even 20 minutes. A lot of people have told me they'd like to get away early. Some have already left. I think that 15 or 20 minutes would be enough just to put some ideas forward, and we can carry on with any conclusions from these 2 days by email after the gig. So,
Rudi, the tea's not arrived yet.
Hasn't it?
Nope.
What time? Sorry, I've got the timing wrong. I thought it was 4 o'clock.
Whatever time it is, it's not here yet.
Do you want to come up, Tim?
Yeah, it's there now, because I'm one of those ones who needs to get away. Where we go from here is Bristol.
All right. Anybody else have a...
Just wanted to it sounds like maybe a reason that that's a good amount of like yesterday using you of your toolkit
Wind stations,
saying now it's obviously
No, yes, no and yes. What I'm saying is basically you have to be careful what you measure. If you want to measure wind, you need to have a constructed wind flow around it, which actually costs a lot of money. Which means you need to have a pole somewhere high, where you don't have surrounding buildings and the rest. And that is a problem. So very often people just stick in an anemometer at the top of the building or top of the mast or whatever, thinking they're getting reliable data in. And the very presence of the building is actually hampering, the data. And because all these analyses for winds, loading, and etc., assume that you will have that kind of wind pressure, unobstructed wind flow, acting on your structure. And anemometers are incredibly. We have an anemometer at the top of the glass tower, which is the second tallest building in Sheffield. And then we compare with really, really unobstructed wind flows at the Met station, which is not far away. And there are differences, sometimes significant differences. And if you ask me which one I should believe more, I would believe always more unobstructed wind data than the one which is measured on the top of the glass tower.
And can you get a live feed from the local metals?
Yes.
I don't know if you saw that one particular slide of Alex's with all the little arrows on. That's actually a site I meant to mention today called XYZ Weather, something? XY Weather. Yeah, and it gives live feeds from all the local weather stations in the country, and it's very good. We use it all the time.
Right today it's worth doing as well.
And things like that is where we could use this seminar as a forum in the future. Tips, look, we found this website that shows what the local weather is. Put it up, disseminate the knowledge amongst the people here. And it's that kind of thing that we can do.
XC weather.
Remember what it's called? I can't remember what it's called. We got the radio man.
And then you click UK and Ireland
No, Martin, you got the radio man.
The other one is Rain Today. It's very good and that gives real-time data and actually does some quite, if you're looking at sort of micro storm cells and stuff, it gives you radar data for wind and, for precipitation. So it would rain today. So if you put into Google, will it rain today? Basically, it started off as a website for, should I take my umbrella to work? But actually, what they do is that you can zoom in as well, and the resolution is quite good. I mean, we were using it at Reading last year, where there's a lot of weather coming to us from the west, and you can actually track little storm cells, and you can predict, oh, is this one going to get us? Oh, it's missing this thing, that's that. So it's quite good. It's not intended as a sort of fine meteorological device for us, but it's brilliant.
Okay, we've had 2 days here. What we were going to do in the last session was work through checklists on site. And with your permission, and because I've had so many suggestions, we're going to not do that and do it by email afterwards. So if anybody's got, I think, a collective checklist from everybody, if you've got your own ideas about checklists and what we need to look for, or questions about what we need to look for, email them to us, seminar@specialstructures.com. We'll look at them, we'll try and answer them. If not, we'll find an expert that can answer them. This is not a free consultancy service, but we'll do what we can on a voluntary basis. Right? And certainly, I would like to get a correlated checklist for stages, for marquees, for steel shield fencing, or whatever, Harris fencing, or whatever. And perhaps we can get some ideas building up and get a database going where we all get the information and not just keep it to ourselves. So, you had a suggestion earlier about resolutions at the end of the... That's why I've asked you on stage.
I'm not sure I had one. I actually had a resolution, but what I think would be very useful...
Is that on?
Yeah, it comes this way.
I think what would be very useful for me, and hopefully some others in the room, is pretty much what Rudi just said. Rather than us writing a checklist, I think the first starting point might be to write a list of questions, perhaps even questions that you'd be a bit scared to ask in an open forum like this to reveal either one's ignorance or the fact that we're still asking simple questions. So, I mean, my proposal, and I've been writing them down for myself all day, thinking, is this something I should be asking somebody else? About the double staking, about what angle the stake should be driven in, how do you connect two stakes together so double staking is effective? All those kinds of simple, on-the-ground checks and balances that we need to know. If you've got 20 minutes to look at a large clear frame, a clear span marquee, okay, don't spend all your time kicking the pegs. It's the corner at the eaves, that's where all the load is. So, check the tie bars there, check the R pins are in there. It's that kind of detail that we should go away having got some learning points. I mean, with no disrespect to, we've heard about £50,000 software here and there, and we're looking at fantastic accelerometers and all the rest of it. Brilliant, it's great. I don't say we don't need that technology and that development. We do. But for next week, the first gig of the year in May or whenever it is, we need to upskill ourselves and make sure that we're consistent in what we say yes and no to. And those of you guys that are out there that are structure providers, you can be consistent in the information you give the clients, and those of you out there who may be clients are consistent in the demands and the questions and the quality control that you exact of your vendors and suppliers. What's not to like? We may all need to, retain some commercial and confidential protection for our intellectual property and for our products, but if we still had the stake test is a perfect example. If we all agreed that actually what we'd measure on the pull tests is a 1 metre stake driven in 800 mil deep and it's 30 mil wide and it goes in vertical and we pull it at 45 degrees, that means when we do it at Glastonbury, it means the same thing. We get a 14 kilonewton pull on that, and somebody did a test at Leeds and they got 17 kilonewtons. We're actually testing the same piece of kit, so we can compare the results, as opposed to them finding out that at Leeds they did the test on a bit of angle line. Totally different deal.
Historical data is always useful, which is the point that Alan was making earlier on about this information being made available.
So my feeling, firstly, my initial feeling is what a brilliant couple of days, and many thanks to Rudi and his colleagues for putting it together, because there have been quite a lot of sessions talking about temporary structures over the last few months. Going back to ILMC and the Event Industry Forum, and there's various places, not even AIF, talked about, but as far as I'm aware, there's never been quite the sort of cut and thrust and quite the quality of people in the room participating in that debate. And personally, I'd really like to get something concrete out of it. See what they get. Even if that concrete thing is no more than an agreed list of questions that everybody's got, and we put it to Rudi, put it to our experts, and we can get some answers back. Brilliant. We've all got a little bit smarter. And we haven't lost any intellectual property, right? We've just used the forum, used the massive brain power here to actually get a little bit further down the route towards, maybe in 5-10 years, I'm looking at computer screens, seeing lovely graphics of, temp pulse flexing or whatever it may be. But until that time, I think we've got an easier resource that we can tap into. I would like to think that we could go away from a fantastically organised couple of days and go away with something very specific and concrete.
I'm going to respond to that by saying, and agreeing with everything that you said, for once. Temporary structures and CDM are almost made for each other. And I know we're not being regulated under CDM, but they're both about how you manage the risk of putting structures up and down. And one of the tools that you use to manage that risk is better analysis tools. That's why we showed you it. One of the tools that you use is better project management. One of the tools you use is better weather forecasting. One of the tools you can use is advanced monitoring, so that you know what the structure's doing in real time, at any time. And yes, they're not available now. Some of these techniques, you can do live load monitoring right now if you want, that's easy. Not every structure needs fantastic, expensive software. But the fact remains is, what every industry professional needs is good tools to carry out its job, and the knowledge and experience to use those tools correctly. We are not health and safety experts. We told you that yesterday morning. We're structure experts. There are people here like Tim and other industry professionals here who know a lot more about health and safety management than we do. This was prompted by the incidents last year. And I said at the festival forum, which one was it, the HMV? Whichever, AIF, yeah. I said, I don't want to be the one who designs a structure that kills somebody. I like to sleep at night. I don't want to be the one who phones somebody up and says, I'm sorry, but your kids ain't coming home. We all have to bear in mind, and we've been accused of scaremongering. Okay, I promise you we're not crying wolf, but if we don't look at this, and you all feel the same way, you wouldn't be here. If we don't look at this and at least say, yes, our practices are good enough, or maybe they're not good enough, or they're definitely not good enough, then I don't think we're doing our job. So the fact that you're all here as in response to what happened last year, I think is good. And the fact that we've all decided that we'd like to take this further, we have had a bit of idea about competency in the industry. And I'm not going to make any announcements, but there are things happened over the last 2 days where we feel there might be a possible scheme that could be implemented as soon as next year. Right? And we're going to work on that, and we will keep you all informed on what's happening with that. I'm not going to say any more because it might not happen. But, and I see competency as being the biggest issue, and one of the main reasons why you can't implement CDM. Because CDM is all about the structure of management and who's responsible, and if you haven't got qualifications, how do they know whether you're competent? So we've got industry professionals who have the knowledge, have got all the experience in the world, and they've got no qualification. That doesn't mean they don't know the job. So we need to find a way of making sure that they have got a qualification to match their knowledge and experience. This is what we're talking about doing. It shouldn't be too hard, should it, if we just get going?
No, I agree. I mean, there have been various industry schemes that have had greater or lesser degree of success, but just to play devil's advocate, not that I disagree with what you've said, but to play devil's advocate, I have got the qualifications, I have got letters after my name, I am a chartered member, I am a registered health and safety consultant, but actually my competence has increased by listening to some of the unanswered questions. You know, what the professor's just told us about positioning an anemometer, for me, is like, holy shit, I do that every single gig we go on.
Yeah, but Schrodinger's got something to do with that one, come on.
We stick it on a pole and go up on the side of a double lift porta cabin and, try and get we will now do something different. So it's that kind of real concrete, like, because you know and I don't.
Can we just clear that up? What the point we're making is if you put an anemometer on the top of a stage, the wind comes off the roof of the stage, it shoots up into the air, and it artificially excites the anemometer and gives you false reading.
Exactly.
That's the point that Alex was making.
Can we just establish if you don't have the luxury of a live feed from a local weather station, and all you've got is a series of poles and a big event site, where is the best place to put it? Good question.
Well, exactly. This is the sort of practical, sweet thing to do. That's not kind of answer. You know, does it go up and out?
Well, it's got to be near enough to where the people are to make it to be relevant.
Is it on a telecoms mast? Is it on the top of a, I don't know, a floodlight on a portable tower, like a CCTV mast? Would those things give us a better reading?
There's no reason why we shouldn't put an extension on one of the masts on one of the big tops or on the main stage.
I don't think you're going to get an answer now, here and now.
No.
You'll know where, how, I mean, it depends on a lot of, it depends on the configuration of the terrain, it depends on the location, where trees are, where other surrounding buildings are, and the rest of it. And you need, I can tell you, the answer is where you have unobstructed flow.
It says that in TDS, it should be in clear air.
Yeah. There's no point in having interrupted flow, which is
Where the geography is not interrupted at all. Because you need to make sure that that analysis, that wind corresponds to what people see is analysis.
And something that immediately came to mind with me when Alex was talking about having to remove the transducers and everything. We've got little mini laptops, and they've got tiny little hard disks that are spinning several thousand RPM. And if you've got anything like a modern one, if you were to drop it, in the time it takes for you to drop it, there's a little accelerometer in there, and it locks the hard disk to stop it getting damaged when you drop it. I'm sure we could find some way of building accelerometers with locking mechanisms so it doesn't get damaged in transit.
Yeah.
Right? So these things could be built in.
Really, back to the wind, the anemometer thing. I mean, one of the issues is that actually what's hitting our structures is interrupted airflow anyway. So if we find an uninterrupted airflow, it'll tell us what's happening generally, and it'll tell us it's fast. But actually what's hitting our structures is interrupted, because it's been under a sheet of steel shield, or it's coming past another fence, or it's coming past the front of the house. So what hits the main stage is already interrupted. So we're never going to get a perfect answer.
Oh yes, you have. There's an easy way to get a perfect answer, Noel.
When you've got multiple holes.
You measure the load on the roof, and you measure that by measuring the strain in the base plates, for example, which is your live monitoring.
If we're trying to predict, the exact point at which, well, we can say 25 metres a second, perfect. But if we're trying to say, have we got 25 metres a second, we might have got a pole, 300 metres that way, perfectly situated, and it's saying 25 metres a second. But the main stage might be getting 35 because it's going past the front of the house, dynamics of the airflow past it, it's coming through the big top. So, I think we used 4 website training last year to get the wind speed. Everyone was different, and the anemometer input was different again, and the anemometer on the main stage was different. So the perfect uninterrupted airflow anemometer isn't actually telling us what's hitting the structures anyway. I'm not trying to be.
No. But that's why we have safety factors. That's why we design structures with safety factors, precisely to take into account this level of uncertainty. Now, what you're doing, if you are having, you're absolutely right. What is hitting your structure is not what is meant. But you don't want to multiply levels of uncertainty. That's all what it is all about. He always designs structures with factors of safety which are precisely designed to look after inaccuracies in loading. So forget about that. But then you can't correct one mistake by creating another mistake. That's the logic. You need to have one reliable piece of information so that other piece of information can work in conjunction with that one.
I totally agree. But the question then is, the perfect uninterrupted airflow I'll stick with Reading again, is going to probably be about 10 metres, 15 metres in the air. But actually, is that the appropriate height? Because the wind speed will vary as you go on the ground.
Well, the average wind speed at 12 metres is 3 or 4 times that at 2 metres.
Yes, so how the hell do we get the perfect place to put the anemometer? So I'm listening, but I'm just trying to think where we put it. Because we've got a radio mast, which is brilliant, but it's like 30 metres up.
There are methods you can use
design is the gust speed that's exceeded 10% of the time at 10 metres high. It's specific at the actual wind load that the number that you actually use is set at 10 metres above the ground.
And perhaps we need some more dialogue on this to really hammer it out so that you understand it. We understand it, we do it day in and day out, and we understand CP, coefficient of pressure on the roof of the structures. Because the temporary structures are never in the same place, it's not like designing for a building, which Alex did with the two towers next to each other. We can't tell you what's going to happen to the structure because we never know what's going to be around it. You have to make it, that's why you need factors of safety and have an allowance so that whatever's around it, it doesn't affect it. But the one sure way of knowing what that structure is doing is live load monitoring. It will give you a warning at 50% of load. It'll give you a warning at 60, at 70, at 80. 80 sounds to me like a good figure to stop what you're doing and run, right? And these are not expensive. He's already said it's a couple of £1,000 compared to the 40,000 people coming to a festival. It's not enormous.
The manometer place, we're not really interested in it at the Met Station 2 miles down the road. Or
It's an indication.
Top of the hill at the side there. We're interested where it is on the stage location itself.
Yeah.
So, it is different. 2 fields away on your radio bus to where the stage is.
Well, this is the one time when, they say if a man's got one watch, he knows what time it is. If he's got 2, he's never sure. Right. This is the one time I would contradict that and say maybe 2 anemometers on different sides of the structure would give you, an average between the 2 would give you more accurate reading.
And don't forget, wind is a statistical phenomenon. Wind is a statistical phenomenon. So therefore, you always you need to be aware of that. The best way to actually handle wind for a particular site is not to measure what is happening over the last 5 minutes or over the last is to actually have like what we've done with Rudi, wind directions, they were established over 30 years, basically. So I'm not saying now you need to have 30-year data for a particular location to know, the nature of the wind and everything else. But you will not, wind. You have to know how to deal with statistically, reliable or unreliable data. The problem in this case is that you can have sudden, freak wind gusts which can blow it off. That's the problem. Now the question is, how often does it happen? In Heathrow, Heathrow location was selected so it doesn't happen very often, but it still does happen. Because if it happens very often, there will be lots of air crashes over there. So this is another awareness. When you're selecting sites for your locations, it will be very nice, ideally. It will be, if you have data for that particular location over the last 20 years, over the last 30. I know it's not done, but this is what serious people do about these things when you need to design and have structures or any kind of process which is where lives are dependent on wind.
So if we're talking about a festival organiser, it would be wise to save and collect the historical data of the weather on site for that particular month of the year. And as the festival goes on year after year, you build up a database of information of exactly what's happening. Last one, we're going to break for coffee.
I did a bit of research with gathering data because I work positioning wind turbines and that sort of thing. Statistical data going back 30 years is available online. It's free. You can get it. It's quite chunky. It's not very good resolution. So if you do get, it's 3 miles an hour average or whatever. You can also get peaks from that. There's technology out there, standard bits of kit that are 10 meters up. It comes to sort of stand, and that does it around the long term. You need that clear space 10 meters off the ground to get any undisrupted area.
We're not saying that site wind monitoring is an answer. It's part of the answer. And we're not saying that historical data is an answer. It's part of it. All of this creates a whole. And all of this is about managing the risk. We keep going back. Event safety is about managing risk. Good management of temporary structures, erection, dismantling, use is about managing the risk. I'm going to wind things up for now, but I'm going to suggest, you're getting off to the tea's ready. I'm just going to pick up. So, we're going to finish things off after the tea break, and the session might be quite short, or it can be as long as you like. But my suggestion is, if you've got any questions, any suggestions, we'll have a final little question and answer session, which was always scheduled. And my suggestion is that any long-term questions we handle by email after the gig. We'll see you in 10 minutes.
I couldn't even tell you what's on next week.
Oh, right. Yes, but they do talk. I've been told they do expectations.
Two.